Okay, hello everyone. So today we are going to be fixing a defect of our recent discussion, a theoretical defect of our recent discussion. So many of the recent theorems that we've proven, including Cauchy's theorem, Cauchy's integral formula, and the consequences of those theorems, in particular the power series expansion result and Liouville's theorem from last time, they all depended on assuming that f is holomorphic, that f is a holomorphic function on the domain that we're interested in. So remember, a holomorphic function is one where f prime exists and is continuous. Okay, so f analytic, that's just assuming that f prime exists. This is terminology that the book doesn't use. I've introduced it because I think it's convenient to have. So we're distinguishing between these two things. So clearly, f being holomorphic, that implies that f is analytic, right? Because f being analytic is part of the definition of f being holomorphic. So one of the really remarkable things about complex analysis is that, in fact, f being analytic implies immediately that f is holomorphic. So just knowing that f prime exists is enough to know that f prime is also continuous. And so all of the theorems that we've proven, actually, it suffices to know that f prime exists. We don't have to assume that f prime is continuous, because that follows that follows logically from the structure of the theory, but we just haven't seen how that works yet, because the arguments are, well, it's somewhat subtle, and at least one of the parts of the argument is somewhat difficult. So we'll be going over that today. Okay, so that's everything on this part of the slide. Okay, so we're removing the hypothesis of holomorphic and going back to just analytic. So basically all of the theorems of complex analysis hold just knowing that f prime exists at every point of a domain. You don't have to assume that it's continuous. Get that for free. Okay. So here's the outline of the argument. Okay, so the outline of the argument, the first step, so we'll be assuming that f is an analytic function on a domain. The first step is that you can prove Cauchy's theorem in the case of a rectangle. Okay, so this is called the Cauchy-Goursat theorem. So Cauchy initially, basically implicitly, was always assuming that f prime is continuous, and it took about 50 or more years for Goursat to realize that one can remove the hypothesis that f prime is continuous and just work with the hypothesis that f is analytic, that f prime exists. So this is Goursat's extension of Cauchy's result, that if you integrate around a closed curve, you get 0. So Goursat provides a proof in the case that R is a rectangle. So we have f being analytic on a domain. There's a solid rectangle inside the domain. So by solid rectangle lying inside the domain, I mean not just the edges. So a rectangle for us means not just the edges, but everything that's contained inside the edges. Okay, so the edges of the rectangle and the interior of the rectangle, that's all contained in D. That's what we're calling the rectangle. And then knowing that, the integral around the boundary of the rectangle, going counterclockwise or clockwise, doesn't matter, is equal to 0. Okay, so that's the first thing. So knowing that f is analytic, we have this weak form of Cauchy's theorem called Cauchy-Goursat. Okay, and then it turns out that remarkably that's enough if you combine it with the following theorem that you see in number 2 here. It's called Morera's theorem. And Morera's theorem says that if you just have a continuous function on a domain, and if you know that that continuous function has integrals around every possible rectangle that's contained in that domain equal to 0, then f has to, in fact, be holomorphic on D. So that's to say that f has a derivative, and that derivative is continuous. Okay, so just knowing f is continuous and having all of these integrals around rectangles being equal to 0, that implies that f is holomorphic. Okay, so that's so knowing that the integral around rectangles is equal to 0 is actually a fairly strong condition that automatically upgrades a function from just merely being continuous to actually being holomorphic. And then you can see how the result that analytic equals holomorphic follows. You just put Cauchy-Goursat and Morera together, right? So basically just you like read them one after the other. So you just sort of suppose f is analytic. Well, Cauchy-Goursat, what does that say? That says that the integral around any rectangle in a domain is equal to 0, right? And f being analytic, well, the derivative exists, so it's automatically continuous, right? So that means that if f is analytic, then by Cauchy-Goursat, it satisfies the hypotheses of Morera's theorem. And then the conclusion of Morera's theorem then is that f has to be holomorphic. So just starting with Cauchy-Goursat, the result of Cauchy-Goursat when f is analytic means that you satisfy the hypotheses of Morera's theorem. And then so the conclusion of Morera's theorem is from that is that f has to be holomorphic. Okay, so that's the proof that analytic implies holomorphic, and as I said above, holomorphic implies analytic trivially, so these are actually the same thing on a domain. Okay, so that's the outline of the argument. There's two phases to it, one being the Cauchy-Goursat theorem and the second being Morera's theorem. Okay, so now we will have to prove Cauchy-Goursat. Okay. So basically, so Cauchy-Goursat theorem. So I just say CGT. And this basically says that the integral around the boundary of a rectangle of a analytic function, as long as that rectangle is contained in the domain where f is analytic, is equal to 0. Okay, so if your R here is contained in D, where D is the domain of analyticity of our function. Okay, so let me give you an idea of how Goursat came upon the argument. I think, well, what I think probably he was thinking. It's a relatively simple observation. Okay, so all we have is that we know that f is analytic, right? So our f here, so f is analytic on D. Okay, so what does it mean to be analytic on D? Well, what it means, so f analytic. So f is analytic, and let's just take some w in D. So what f analytic means is that f prime exists at every point in the domain, right? So f prime of w exists. Right, so we have f prime of w exists. And what this means is that the limit as z approaches w of f of z minus f of w over z minus w minus f prime of w, so this equals 0. Right. Okay. And this limit, I mean, we can put this limit wherever. We can put this limit with just that there, or we could just put the limit, since there's no z in the other term, we can put the limit there like that. So it'll be convenient to have a name for this quantity here. So I'm just going to call this epsilon sub w of z. So saying that f is differentiable at w, that's just equivalent to saying that the limit as z goes to w of epsilon sub w of z is equal to 0. Okay, what I'm going to do now is rewrite f of z here in terms of, well, so I'm going to take this equation that I have for epsilon sub w of z, that's equal to this expression. I'm going to re-express that just algebraically in terms of f of z, because this just turns out to be kind of interesting way to think about differentiability. F of z is equal to f of w plus f prime of w times z minus w plus epsilon sub w of z times z minus w. So let's take a look at this and see what this is telling us. So what you can notice here is that this is a linear polynomial. In z. So here we're thinking about w as being fixed. That's the point where we're taking the derivative. And then z is varying in the neighborhood of w. So z is our variable. W is just fixed. So if w is fixed, this is just a number. And this f prime of w, that's just a number. And w is just a number. The only variable we have is here. And that's where our variable z is. So this is just a linear polynomial in z. And then we have all of this other stuff here. Right, so basically saying that f prime of w exists, so saying that f prime of w exists is equivalent to saying that f of z is equal to a linear polynomial in z plus some error. Okay, so the error is this epsilon here. That's why I called it epsilon. Some error times z minus w. And where the error, and so remember the key that this limit up here, that's equivalent to this limit over here, right? So this tells us that the error goes to 0 as z goes to w. Okay. So f of z near w is a linear polynomial in z times something small, right? So this error is going to 0. So the closer z is to w, this error is very close to 0. And also z minus w is very close to 0 as well when z is close to w. So this extra stuff here, the part that's not in the linear polynomial, is sort of extra small. Okay, so this is extra small, doubly small. Okay, so basically saying that f prime of w exists says that f of z near w, f of z is a linear polynomial in z plus some extra small stuff, right? So basically that f of z is basically for all practical purposes linear when you're very close to w, right? Which is just, this is just saying that f is linearly approximated very well when you bring z close to w, right? So that's the meaning of f prime of w existing. So this is very much like the intuitive interpretation in calculus, right? So your function is differentiable, means it has a linear approximation, right? You can approximate it by the tangent line. So this is the technical statement of that in the complex case here. Okay, so it's in spirit very much similar to what you've seen in calculus. F prime of w exists means that near w, f is a linear polynomial plus some error term times a linear term. So you have this extra small stuff being added onto a linear polynomial. That's what f looks like near w. Okay. So what Goursat observes, so Goursat's main observation is that if let's take a small rectangle, so take a small rectangle R, going around with, so W is inside the rectangle. Okay, so basically what Goursat observes is this linear polynomial here, right, that this is holomorphic. Right, so we know that its integral, so if we take an integral around a closed loop of that part, that's 0, right? So the integral, so take a small integral, take a small rectangle, linear polynomials are holomorphic. So the integral around the boundary of this rectangle of f well, that's going to be, so we're going to have the integral of the linear polynomial around that closed loop, but that's going to be 0 by Cauchy's theorem because we have a holomorphic function, right? It's stronger than analytic. And then we're just going to get the integral around the boundary rectangle of this error times linear. And again, this integral, this should be very small. So this should be very small because the quantity that we're integrating is very small. Okay, so sort of first observation is that by Goursat is that if we integrate around a rectangle, our analytic function, around a small rectangle, then we expect the value of that integral to be very, very small. Okay, because because of the linear stuff just goes away when we integrate around that closed loop, and then we're just left with the integration of the error term. And so it'll probably be helpful for us to estimate how small this integral is. So the integral around this rectangle so by the max length inequality, this will be less than or equal to the length of the boundary of the rectangle times the max on the boundary of the rectangle of the error times norm of z minus w. And so let's see, this norm z minus w, if this is our rectangle, our w is going to be in here somewhere, z is going to be on the boundary. The worst this distance could possibly be is that diagonal distance there. So norm z minus w is less than or equal to the length of that diagonal. But that diagonal is just one side of this triangle here. So by the triangle inequality, the length of that diagonal has to be less than or equal to the half of the perimeter of this rectangle. So that would be So that's 1/2 the length of that boundary. So we can replace this norm z minus w with, so you get length of the boundary of R squared, and then times the max, you can just say the max over the rectangle of this error. And we can call this here epsilon. And the length of the boundary of the rectangle, the perimeter of the rectangle, squared. It turns out later it'll be useful to realize that's less than or equal to some constant times the area of the rectangle. Okay, so we can always just write, so this constant so what we're doing here is writing that the length of, so the perimeter squared over the area, that's some constant. Yeah, and so one kind of important thing to note about this constant is that if we were to rescale our rectangle by some constant factor, so we had a similar rectangle, then this c would be the same. So this c here, this is invariant. So maybe I'll less sophisticatedly say it's the same constant for all similar rectangles. Okay, so that'll be worthy of note later. Okay, so we obtain this estimate here, that this integral around this small rectangle of this error times z minus w, that can't be any bigger than the max of the error on the rectangle times the area of the rectangle, and then times some constant. So that's for a small rectangle around this point w. So what happens for some arbitrary rectangle? So we have a rectangle R in our domain, and what Goursat wants to do is subdivide this rectangle into smaller rectangles until the rectangle is small enough that the error term is small for the derivative at some w. So basically what Goursat wants to do is, so we subdivide this rectangle, the original rectangle, into similar rectangles. And what he's hoping is that after you subdivide, that maybe there's let's say there's a W1 here, such that the error at W1 of z is less than epsilon in the smaller rectangle. And what you're hoping is that this is true for every one of these smaller rectangles. And now maybe it's not. So if it's not, then what you'd have to do is subdivide further. So then you would subdivide further and then hope that in each of these smaller ones you can find a W2 and a W3 and a W4 and a W5 such that the error at W sub I of Z is less than the epsilon you have in mind. And so you might have to divide this one like this, and you might even have to divide this one even further before you found your points W. Okay, so then you have, so these are all W sub J. So you're looking to subdivide the original rectangle, into smaller, similar rectangles, so that there are points in those smaller rectangles where the error coming from the derivative at those points in those smaller rectangles is smaller than some given fixed epsilon. And then, so what Goursat notices is that our original rectangle, if we integrate around the boundary of that rectangle, our f of z, that's the same as the sum around the boundaries of all of these smaller rectangles. So if I call these smaller rectangles r sub I, and we integrate f of z around all of those smaller ones and add them up, that's the same as just the integral around the boundary of the original rectangle. And the reason for that, that may seem weird because these smaller rectangles have all of this extra stuff, right? So like this line segment here does not appear in the it's not on the boundary of the original rectangle, so it sort of doesn't appear in the original integral. But like that segment there is, so let me illustrate here. It shows up when you go around this blue rectangle here, right? So when you go around that blue rectangle that way, and it also shows up when you go around this red rectangle. Right, so you're going around every rectangle counterclockwise here. So it shows up when you go around that red rectangle counterclockwise. But you see what happens is that along that segment, it occurs in the opposite direction that it did from the when you went around the blue way. Right, so in blue, you're going up that segment. In red, you're going down. And you can see that that happens for all of the other interior segments. So the interior, so integrals over interior segments cancel. Right, and so you can write this integral around the big rectangle as a sum of a bunch of integrals around the smaller rectangles. And now we see that, so if you can do this, right, so if you can find these, so if you can subdivide your rectangle into these smaller, similar rectangles where you have these points where the error is small, then you can estimate your original integral. That's less than or equal to the sum, or I, of, so you have the absolute values of, so this is using the triangle inequality. And then the ML inequality applied to this, you have the sum over the i's of the length of the boundary Ri. Oh, sorry. So this f of z, remember you can replace, so you can replace with epsilon sub wi of z times z minus wi, right? Just as we did above. Right? So if you do that replacement, then you have, again, by the ML inequality, max of the boundary Ri times epsilon, so wi of z times norm z minus wi. And this is, now we're in the exact same situation we were above, right? So what we came down to is that this is less than or equal to 1/2 the length of boundary Ri squared times epsilon, because these, so we're supposing we can find these wi's so that this inequality over here, in all the smaller rectangles, the error is bounded by this fixed, this uniform epsilon. And because all of the rectangles are similar to the big rectangle, so all of the little rectangles are all similar, right? So they all have this same, the ratio of the perimeter squared to the area is the same c. So we can write this is less than or equal to c over 2 times the area. Oh wait, I lost a sum over I. Sum over I. Sum over I. Area of r sub I, and then times epsilon. And well, the sum of all of the areas of the little rectangles, that's the area of the big rectangle, right? So this is c over 2 times the area of r itself times epsilon. Right, but this epsilon was arbitrary, right? So so this right-hand side here, so as long as we can, so I'll say it this way, as long as we can make this estimate for arbitrary epsilon greater than 0, it follows that the integral around the rectangle, the big rectangle of f of z dz equals 0, right? Because so you have, because if this holds for arbitrary epsilon greater than 0, we can make this number arbitrarily small, right? But that's bounding this quantity here above, and this is bounded below by 0. So if that non-negative quantity is less than any arbitrary positive quantity, then it must be 0. Okay, so as long as we can push this estimate through for arbitrary epsilon, it will then have to follow that the integral around the rectangle of f is equal to 0. Okay, and so that epsilon, so where did that epsilon come in? Right, so where does epsilon come in? Where epsilon comes in is here. So where the epsilon came in was we wanted to make our errors in all of these rectangles smaller than epsilon, than that same epsilon. So that epsilon comes in when we want to claim that we can take our original rectangle and break it up into a bunch of smaller rectangles such that in those smaller rectangles we can find points where the error of the derivative with respect to that point is less than epsilon throughout each of those little rectangles. Okay, so if for arbitrary given epsilon we can subdivide our rectangle into a bunch of small similar rectangles, with this property that the errors are smaller than that epsilon in each of those smaller rectangles, then it will follow that we have the Cauchy-Goursat theorem. Okay, because then we can push this estimate through here for arbitrary epsilon, and it follows that the integral around the whole rectangle has to be equal to 0. Okay, so we just have, so where does epsilon come in the estimates? Okay, so thus Cauchy-Goursat will follow from the next lemma. Okay, and so the next lemma is what I'm going to call, this is just a name I made up, Goursat's uniformity lemma. All right, so the lemma says if epsilon greater than 0 is given, and f is analytic on a domain D containing a rectangle R, then we can subdivide R into similar rectangles R sub I, such that there exists Wi in R sub I satisfying that the norm of f of z minus f of wi over z minus wi minus f prime of w of I, which equals the absolute value of epsilon sub wi of z, is less than that epsilon that was given in the beginning for all z not equal to wi in R sub I. Proof. If there is a W in R such that epsilon sub W of Z absolute value is less than epsilon throughout R, we are already done. If this is not the case, subdivide R evenly into 4 similar regions. If the required W exists in one of these regions, great. Don't subdivide anymore. If not, then subdivide each of the offending regions into 4 similar regions. Okay, so we're just taking our original rectangle. If we couldn't find a W in the original rectangle, we subdivide into 4 regions. Maybe after we do that, maybe we find W's in those 2 regions, right? So W1, W2. Maybe not in the other ones, so we just continue and subdivide those and look for the required W's in each of these smaller regions. And then maybe we find them in some of them, but then maybe this other one we'd have to continue to subdivide. And continue in this manner. So we either succeed at some point, or we continue to subdivide and find a sequence of rectangles so the sequence would start with R itself and then inside of R. So in our picture over here, so let's say, so in our picture over here, so we started with R, and we didn't find a W that worked in R, so we had to subdivide into 4 regions. We found W's that worked in 2 of them, but we didn't find them in the bottom left and the top right. So let's just focus on the bottom left here. Then in that one, the top left of that had to be subdivided again, right? And then maybe in this one, if we're not succeeding, every time we don't succeed in finding w's, we have to be moving into a smaller subregion, subrectangle of the rectangle we're working on, and continue going down further and further, subdividing and looking at the places where we don't find the w's. And so that's the basic idea. Find a sequence of rectangles, starting with R, and then you got R1, R2, R3, right? So each rectangle is a quarter of the size of the one preceding, right? Oh, whoops, sorry. Okay, so you get this descending, shrinking sequence of rectangles. And if you have a shrinking sequence of rectangles like this, so the rectangles are shrinking down, they're all nested inside of each other. There's got to be a point there in the intersection of all of those rectangles. Okay, so there is, in fact, a point Z0, which is contained in the intersection of all of these rectangles. Let me just call this, let me call R R0. So the intersection from I equals 0 to infinity of all of these rectangles. And this follows this is actually really a property of the real numbers, that the real numbers are complete. They don't have any holes in them. So this sequence of shrinking rectangles couldn't be converging on a hole. So I won't fully justify that. You'd study that in an analysis class. So I'm not going to talk about that anymore here. Completeness of the reals. Okay, so now Z0 is in all of these rectangles. So it's in R sub I for all I. And then what was the thing about these R sub i's? So these R sub i's, it was the case that no matter what point you take in that rectangle, it's not the case that the error is less than epsilon for all the z's in that rectangle, right? So that means that if it's not the case that the error is less than epsilon for all of the z's, there must be some z sub I, or maybe I'll say zeta sub I. So Z0 is in R sub I for all I. So there are zeta sub I in Ri such that the error at Z0 of zeta I, that in norm is bigger than or equal to epsilon, right? Because that was the characteristic property of the R sub I, is that for any point in there's got to be at least some other point that ruins that inequality. Right? That's how we constructed this descending sequence of R sub i's, where we weren't succeeding in making our inequality work out. Okay, well, so now the key point is going to be that these zeta sub i's are actually converging to Z0. So but zeta sub I is converging to z naught since the rectangles r sub I are getting arbitrarily small. And so the rectangles are shrinking by a factor of a quarter, the area of them every time. So the length is halved and the height is halved of each of these rectangles. So these zeta of i's are in these rectangles, and z naught is in these rectangles. So zeta I and z naught can't be any further away than the diagonal of these rectangles, but that diagonal is shrinking by a factor of 2 each time. So that's getting arbitrarily small. So now we have these zeta i's, they're tending to z naught, so they're limiting to z naught, but the magnitude of this error at z naught of zeta I, that's bigger than or equal to epsilon, right? But our f is supposed to be differentiable at z naught, right? So that error is supposed to be going to 0. And that's not happening. So the error is supposed to be going 0 the closer you get to z naught. But that error is not going to 0 for the sequence of zeta i's that are going to z naught. So that's a contradiction to the fact that z naught is, that our f is differentiable at z naught. But zeta I goes to z naught since the rectangles are getting arbitrarily small. And f is supposed to be differentiable at z naught. Thus, it should be that the limit as z goes to z naught of the error at z naught, z, is equal to 0. However, the limit as zeta I goes to z naught of the absolute value epsilon z naught of zeta I is not equal to 0, since epsilon zeta naught, or z naught of zeta I, is bigger than or equal to epsilon in absolute value. So this contradiction means that we must eventually arrive at the required subdivision of R. Okay. All right. So that completes the proof of Cauchy-Goursat. So that was the lemma that we needed. So just as a sort of recap of the argument. So basically, Goursat says, take your rectangle. You're integrating f around the boundary of this rectangle. Take that rectangle and break it up into a bunch of smaller, similar rectangles. And your integral over the big rectangle is going to be the sum of the integral over those smaller rectangles. And in these smaller rectangles, you can choose them so that there's a point inside where the error coming from looking at the derivative of our function f at that point, such that that error is less than epsilon in all of these smaller rectangles. And if that happens, if all those errors are less than the same uniform epsilon, then we can estimate that our integral that we're interested in is no bigger than some constant times the area of our rectangle times epsilon. And since we're allowed to take, since that epsilon was arbitrary, then the magnitude of our integral has to be arbitrarily small, and therefore it must be 0. Okay, so that's the full argument. And so basically Goursat's idea of looking at small rectangles comes from the fact that that in a small rectangle near a point, you have this linear approximation kind of thing. So the integral around your rectangle of f is just going to be the integral of the error, because the linear polynomial part is going to drop out because that's holomorphic. Okay, so that's kind of a broad overview recap of the argument. All right. So that's the Cauchy-Goursat theorem. And remember, so that said, analytic functions, the integrals around rectangles of analytic functions are 0. And the next result is Morera's theorem. And so remember, Morera's theorem, what that said is that if f of z is continuous on a domain D, and the integral around any rectangle of f of z dz equals 0, so that's for every rectangle R contained in D, then f is holomorphic. On D. Okay, so here's the proof. So the main idea of the proof is to find an antiderivative of f, a local antiderivative of f. Okay, so the idea is that in a disk, so we fix a z, let's fix a z naught. So we're going to fix z naught in D and a disk around z naught of radius r contained in D. Now the idea is to construct an antiderivative say capital F for f on this disk. Okay, so if we can do this, we're done. And why is that? Well, if we can do this, so if f is big F is an antiderivative, so we have f prime equals f, and f is continuous. that would imply that capital F is holomorphic on this disk. And so we'd be able to expand F in a power series. So that would imply that F of Z is equal to some an z minus z naught to the n. And that would imply that, and this is on the disk. And that implies that little f being the derivative of big F is the sum n equals 0 to infinity n an z minus z naught. I guess this is 1 to infinity, n minus 1 on d z naught r. Right, so then F, more than being holomorphic, well, of course, we know holomorphic implies power series. We see, directly that F has a power series expansion. So this implies, F is infinitely differentiable. In particular, F is holomorphic. So that means F is holomorphic on this disk. But holomorphic is just a property of a function near a point. So the fact that it's holomorphic in the disk at that z naught, that means it's holomorphic. And this z naught is arbitrary, so that's going to be holomorphic anywhere in D. Right? So anywhere in D, we can put a little disk around our point and then show that F has a derivative, has a power series expansion. So F is going to be holomorphic everywhere. Okay, so construction of the antiderivative. So how we do this is analogous to calculus. So analogous to fundamental theorem of calculus, part 1. So what we do is, so we have our disk. So our disk around Z naught, there's our point Z. So we're going to define capital F at Z by integrating. So what we're going to do is we're going to integrate along a path, F of zeta d zeta, and the path is going to be you first go horizontal over to being sort of vertically in line with Z, and then you go up the vertical to Z. Okay, so gamma, so this is gamma 1 here, and this is gamma 2 here. So gamma equals gamma 1 plus gamma 2 as pictured. Okay, so we always do the horizontal. So you integrate along the horizontal part first and then the vertical. To travel from Z naught to Z. Okay, so this is a well-defined function. For any Z in the disk, there's a unique path that goes horizontal and then vertical. So the horizontal path might be to just sit still, right? So if your Z is directly above Z naught, you might not have any horizontal component at all and just go vertical. But in any case, so we're allowing sort of the path that doesn't go anywhere to be your gamma 1. But this gives us a well-defined function, and So all we have to do is, so we need to show that capital F prime of z is equal to little f of z. Okay, so in order to do this, we have to show, so i.e. that the limit as h goes to 0 of f of z plus h minus f of z over h minus f of z equals 0. Okay, so the first thing we're going to do is look at f of z plus h minus f of z. So I'll illustrate this in the picture up here. So let's say our z plus h is like right here. Okay, then f of z plus h, let me use a different color to emphasize. So f of z plus h, you get that by integrating along this horizontal here and then going up to z plus h, right? Okay. All right, so that's f of z plus h, and then you're subtracting f of z. And what's f of z? Let me see if I can clean up my picture a little bit. So f of z is going along this horizontal and then this vertical, right? But minus f of z, well, that's the minus is going to switch the direction of each of those integrals around. So that would be like going down along this vertical. So it's like going backwards along the curve, right? And then back along that horizontal segment there. Right? And what you can see is that these, so this part here in yellow, that cancels out because the blue one is going right and the red one, the red part along there where they're flushed together is going to the left. And so those two things cancel out. And so f of z plus h minus f of z is this is now this green. So it's integrating our little f around this green curve here. Right? Okay. And so the key thing now is what we can do is I'm going to insert another point here, which is at the same vertical level as our point z. And if we, so our, yeah, so we just added an additional stop here at this black point on this green curve. And now what I want to do is, yeah, let me reintroduce. I only have so many colors here, but I guess I'll use yellow. That's all right. So look at this first part of the curve in yellow. And then that second little bit in green there. The yellow part is, that's three legs of a rectangle, right? So the yellow, it goes down and then to the left and then up. And then if I were to go across like this, that would make a full rectangle, right? But the assumption of our theorem is that this f satisfies that any integral around a rectangle is equal to 0 in the domain where our function is defined. Right? So that means that these three yellow legs plus the red leg is equal to 0. Right? Well, that means the three yellow legs, that means the three yellow legs are equal to the to negative of the red leg there. But the negative of the red leg is just the red leg going backwards. Right? So those three yellow legs are equal to this new red leg where I go across like this. Right? Okay. So all told, f of z plus h minus f of z is it's this integral around the yellow legs plus the short green leg. But we can replace the integral around the yellow legs with the integral along this red one, and then plus the green one on the top of that. So if we, maybe I'll just, so I'll call this sigma 1 here, and this green one, that's sigma 2. Okay. So f of z plus h minus f of z, that's the integral along sigma 1 plus sigma 2 of f of zeta d zeta. Okay, and now we're ready to look at this limit. So the limit as h goes to 0 of, we have 1 over h times, so this is what we're trying to show, is this equal to 0 here. So let me just delete this. Yeah. Okay, so this is equal to, so we have the integral along those two sigma paths, f of zeta d zeta, minus f of z. Okay, and now what I want to do is I want to get the integral, so I want to express f of z as an integral. Remember, z is just just this fixed point, right? The integration variable is zeta. So what I can do is, so let me leave myself some room here. So I basically I want to sort of insert an integral here, right? Because f of z is just some constant. So I have this. So if I integrate the constant f of z dz, d zeta. So if I integrate that constant along that curve, well, the antiderivative of a constant, so I can evaluate this integral just by using the fact that I know the antiderivative of a constant. It's just that constant times zeta, and then you take that antiderivative and you plug in the endpoints and you take their difference, right? But the endpoints of this curve, sigma 1 plus sigma 2, is z plus h and z, right? So I would just be taking the difference of those two things, and that's just h, right? So the integral of this constant here is h. So what I have to do is I have to divide by an h here in order for this integral divided by h to be equal to f of z. Okay, so you just sort of want to get an integral involved here. You just have to mess around and figure out the right thing to insert in there so that you get f of z. Okay, but you can check that that's correct, and then that's nice because you have the h's there. So what you find is that this is equal to the limit as h goes to 0 of 1 over norm h, then times the norm of the integral along sigma 1 plus sigma 2, f of zeta minus f of z d zeta. And then by the ML inequality, this is less than or equal to the limit as h goes to 0 of, the sigma 1 curve, the length of that is the absolute value of the real part of h. And the sigma 2, that's the absolute value of the imaginary part of h. and then we have that divided by h, and then we have times the max, so no worse than the max of f of zeta minus f of z. And, well, yeah, so that curve there, that whole curve is contained in the closed disk around z of radius h, right? So we can just say max over the closed disk around z of radius norm h. Okay. So we have limit as h is going to 0 there, but this, the real part of h, that's no worse than h itself, the length of h, and also the same thing with the imaginary part, because this is just a right triangle. So the non-hypotenuse sides of a right triangle are always less than or equal to the hypotenuse side. So this is actually encircled there as less than or equal to 2. So that's bounded by a constant. And then this maximum, as h goes to 0, right, then zeta is getting close to z. But f is continuous, right? We're assuming that f is continuous. So this maximum has to be going to 0. So this equals 0 because f is continuous. Okay, and that completes the proof that the derivative of capital F is equal to small f. And then as before, as I summarized above, that implies Morera's theorem, that this little f function is goes from continuous to holomorphic just by knowing that the integral around the rectangles is equal to 0. And the only place we use that is to rewrite this integral. Basically, where we use that is in this f of z plus h minus f of z to rewrite that in a nice way. Okay, so that gives us Morera's theorem, and then combined with the Cauchy-Goursat theorem, that implies those two imply that analytic functions are holomorphic. Okay.